Thanks, Flora, for the kind introduction. I'd like first to express gratitude to all this community and for you to give me this scene where I'll get a little bit away from the announced title. As you may have noticed yesterday, Nick talked about axon spikes measured in the cortex, which we strongly believe is feasible and should become routine. Therefore, I am entitling this talk as Axonal Arbors with Neuropixels. And so my talk will be in three different parts. First, what we have been doing in the superior colliculus as detecting axonal arbor and all the other features. Then I'll move into V1 as in the cortex being putatively more interesting to more neuroscientists in order to end in the little amount of time that we have with concluding remarks, tips in order for people to be able to move forward. And so, long story short, axonal arbors are the reflect of long-range axonal synaptic contact. And so that's why we call them arbor, and they are basically double peak waveforms that are already present in your data. What I will use a lot is these kind of heat maps, where in blue are illustrated the negative peak of the waveform, in red the positive part of it, where every single line is a single channel, which as illustrated here in orange is very much of a double peak where it is detected. And the advantage of this kind of representation, where you look at the 384 channel of these Neuropixel 1 recordings, is that you can see the actual extent of the compartments that you have been detecting upon. And so what is very particular with the retinal ganglion cell axons is that they are penetrating in the midbrain through a very, very flat plane, as the superior colliculus is, and as illustrated very nicely in this paper from the Barres lab. All the red staining are axons from the retina. The green ones is just one subtype, which very nicely illustrate how planar these projections are. And so somehow, by chance, as we started to study the physiology of the superior colliculus, we went there tangentially. We just mean to really go through in a single flat angle, which can be of a difficult prep, which by chance captures this axon very nicely and actually aligned with this axonal projection, where I cannot stress this enough. These little blue lines that you see here literally is in the physical space 2 millimeters of tissue. By opposition, in contrast, you can see here the same kind of representation for a normal superior colliculus neuron with a classical depolarization followed by hyperpolarization. And so in order to sustain our claim that these double peak waveforms are made of axonal terminal responses, postsynaptic responses, and the axonal projection, which we believe the Neuropixel Ultra can capture, we went through several lines of control, the first of it being pharmacological confirmation. Similarly to what Nick explained yesterday, injecting Messimol locally in the superior colliculus abolish all classical somatic spike activity. So all these normal spikes are gone, as shown here. And then in the consequent injection, in the superior colliculus morphology and anatomy is simpler, so it makes this kind of approach easier to inject TTX directly in the retina, which this time abolish all the activity of the axon. In addition, we also use in a separate set of experiments a cocktail of synaptic blocker, which, as you can see here, literally abolished the rebound, which help us and support the claim that this is of postsynaptic origin. In addition, we also look at the physiology as of two neighboring axons, which are independently detected on the probe of the same visual type. This is important. You will see that the receptive fields are very close by and actually organized in a pattern as in the retina. But the argument that we raise here is that if you look at the cross-correlation between these two axons, you will see the symmetric double peak cross-correlation, which is a classical hallmark of functional gap junction coupling, which is known to be present in the retina. Last but not least, when you have an axon, you have neighboring neurons, you would expect them to be connected. And so that is most of the topic of this first paper, where we looked at functional connectivity in order to see how spikes are transmitted, which will be identified by a monosynaptic delay in the cross correlation, or a peak at the monosynaptic delay in the cross correlation. But I will spare you this detail in order to focus more on how to detect axons and what can be done with these axonal arbor measures. The first being that the great work that has been done by Caroline Guerre here, who finished a PhD last year and who combined this tangential neuropixel insertion in the superior colliculus with optotagging, looking at the connectivity to inhibitory neuron, and then a bit of a more of a computational study from Kai Lun looking at short-term plasticity, where I'm here just showing the potentiation of the second peak of this double peak waveform, which potentiate more for short-term ISI, where, long story short, I like very much the conclusion of this paper as of short-term plasticity being a three-stage process: dendritic potentiation, dendritic integration, and somatic nonlinearity. Anyhow, I will quickly jump here to this intermediary conclusion, as I would like to speak about also of the cortex, to remind you the very few criteria that are important, if not critical, to make a good axonal arbor measurements. First of all, a low noise level in the system, which means a good grounding of the setup and a not noisy reference channel. The two should be independent. Second of all, a good head fix preparation, a calm animal, no bleeding, a good tissue, which you will very quickly observe by looking at the signal yourself, seeing that you have very nice units, big amplitude, etc. And then it's very simple. You take a small recording sample, you just put it in the clustering pipeline, and then you just look at yourself how the templates, how the waveform are coming out of it. And the axonal arbor are the double peak, because they are followed by postsynaptic responses. And so usually we focus on having a first symmetric short duration negative peak, followed by a second longer negative peak. I will then move a bit away from the superior colliculus, because we have insights that actually this kind of technique could be applied almost anywhere else in the brain where we know that they are long-range axons. And so for that, I would like to speak a little bit more on the primary visual cortex, as indeed there were an incentive from this amazing paper a few decades ago using paired recordings, where they already identified a first peak from the axon, a second from the sync, which has been further confirmed using extracellular approaches in the cats from the Meffin lab, where we wanted to know whether it is possible in mice using Neuropixel, and by matter of fact it is, again using these tangential insertions, poking the brain in a weird way. We report in this follow-up paper that this double peak waveform can be observed in the visual cortex, and so putatively elsewhere. We believe everywhere where the thalamus project, which literally means most of the cortical areas. Anyhow, I need to highlight that for the cortical axons, or this double peak in the cortex, that the amplitude, here shown in blue and purple, is super small, and the spread, or I should say the spatial footprint, is super large. Both of these features were already known, which is also an explanation why people usually don't report them and don't get them, because it's a super small signal. Therefore, you need to have a good recording condition. Anyhow, this is visible. All the controls, and there are more for this cortical kind of axonal arbor, are present in this article. For the sake of time, I will move to my next and last part as of the tip and the reproducibilities that we really look forward to, where I'm very happy to report that we have a first reproduction outside of the lab in Paris, thanks to Flora Boutet in Nathalie Rouache lab, with the great help of François David, where they poke Neuropixel vertically in the superior colliculus and still report these double peak waveform. And so it's very easy. You make a recording, you put it in your pipeline, you take all spike times of what you believe is a double peak waveform, and then you average your raw signal based on that. And we have the script, we gladly will share. This is what they observe poking vertically. In addition, we also looked in V1, where in our own data, we have been able to observe by scrutinizing with many details some double peak waveform in some vertical insertion. And so putatively, we are about to claim that every vertical neuropixel recording can have this kind of waveform if you are able to trust these very small signal. I also need to speak about things that may look like axonal arbor, but that aren't. And so this is a supplementary figure or an extract from the supplementary figure from this paper published last year, where we reported the kind of waveforms that you will be able to observe if you look for very small rebound. And as illustrated here in what may likely be a small footprint neuron as of an en passant neuron or node of Ranvier, as as the Steinmetz lab have very well characterized. There are also some interneurons, which are at least a putative interneuron because the waveform is narrow, which are followed by a tiny little rebound, which is of a small spread, a small spatial extent. We believe that these criterion are a very good criterion to use to reject potential multiple peak waveform from being an axonal arbor and a dendritic response. Last but not least, we have developed tools within the lab, mostly in Kilosort 2.5. Kilosort 4 is work in progress, where we hijacked the plotting of the very nice pipeline and the very nice plotting from Kilosort to really stress out the plotting toward axons, so that within a few minutes you record, you look at it, and thanks to this plotting, you will be able to address whether or not they are axons. This is here an illustration from the double peak waveform in phi. And so I will end by acknowledging the people without whom this work would not have been possible. Jens Kremko, not holding the head of a master student, but a toy in one of our social. The Schmidt Galaxy have joined since, and very smart students that I'm working with, building, establishing my own lab. And so as a take-home message, I would like to thank you for your attention, to thank Neuropixels to be that good, and so indirectly all the people working in the background, and there are many. This very amazing community, the Slack. And so if you were to have any question of any interest, you will find our email address.